Is everyone ready? Let's get ready for chemistry! In a previous video about galvanic cells, we talked about how we can add these two half reactions together, and when we add the half reactions together, we get the E0 of the cell. But when we add the half reactions together, even though we have to multiply the silver reaction by 2, we don't multiply the cell potential by 2. The reason for that is delta G0 equals negative NF E0. So if I have the cell potential and I want to find delta G0, N is the least common multiple of the number of electrons being transferred. So when we multiply, so we do multiply it by 2, we just don't do it here. We do it here. And then Faraday's constant, which is 96,485 coulombs per mole of electron, and the moles of electrons cancel. The cell potential, positive 1.56 volts. Now you'll notice coulombs and volts don't cancel. So a volt is a joule per coulomb. And that cancels. But delta G needs to be in kilojoules per mole. So the delta G0 for this reaction is negative 301 kilojoules per mole. This makes perfect sense. A positive cell potential means the process is spontaneous, and a negative delta G0 means the reaction is spontaneous. Or thermodynamically favorable if you're getting ready for the AP chemistry test. If I want to find K, I can relate K to E0. Like so. But what is T? For E0, standard conditions must be 298 Kelvin. That's different for standard conditions for a gas. Standard conditions for electrochem and thermochem is 25 degrees Celsius, not 0 degrees Celsius. So STP for gas is 0 degrees Celsius, but STP for everybody else is 25. I could plug in a different temperature, but the not means standard conditions. So if I plugged in a different temperature, it would necessarily be an approximation. Everything cancels, as well it should. K should not have units. Oops. Looks like I dropped a negative. Oh, but that doesn't look right to me, because that would give me a small k. Looks like I actually dropped 2 negatives. So this should actually be positive. And that makes sense to me, because if the process is thermodynamically favorable, then the K should be product favored. If the K was small, that would be reactant favored. That would be non-spontaneous in the forward direction. So for this set of half reactions, that's how I would find K and delta G0. For this one, I had to multiply the iron half reaction by 5. This allows me to cancel 5 electrons with 5 electrons. But I didn't multiply the cell potential for this half reaction by 5. We take that into consideration when we do N. So delta G naught equals negative NF E naught. Delta G naught equals negative what? 5. The cell potential was positive 0.43 volts. But for delta G, we're going to need the joules per coulombs rather than the volts. This is a really awkward number. That's the reason why we always convert this into kilojoules. But because our cell potential has 2 significant figures, we need to be rounding our delta G naught to 2 significant figures. If we're trying to find K, for this process, the least common multiple of electrons was 5. The cell potential, 0.43 volts. Let's put a positive on that so we remember that we didn't drop the sign. And let's make a line that's straight since we can. The R that we want is the one with joules in it, so that the units will cancel. Again, we're using 298 Kelvin because we're at standard conditions. Everybody cancel now. The voltage is positive, so it's spontaneous in the forward direction. So the K is large because it's product favored. Let's see, I want to find the delta G naught for this reaction here. I have a couple of cell potentials. If I add them together, that'll give me the E naught of the cell. But it doesn't tell me the number of electrons being transferred. That's given by this right here. With 2 significant figures in my cell potential, I should be keeping 2 significant figures in my delta G naught. So that's how you find delta G naught and K.